Alright, so let's look at a example for rates of change. So we've been given a formula that looks like this. We have, when that goes away, that looks like this. We have A being equal to S 1 minus e to the power of minus k t. And what this formula is alcohol concentration after a certain amount of time for something that might be like fermentation for a wine. So S is our sugar content. We don't know what K is, but T is our time in hours. So what we need to, the first part of this question asks us to find what is the alcohol concentration when time is equal to 0. And we've been given here, we've got K that we don't know. We don't know what S is, so we haven't been given either one of these two numbers yet. But we're trying to find what A is when T is equal to 0. So let's just try it and see what happens. It's also worth noting that in this particular question, T is going to be greater than or equal to 0. So let's substitute T in and see what happens. So A is equal to S 1 minus e to the power of minus k times 0. Alright, you might start to think or recognize what's going to happen here. Well, let's work it out. We've got 1 minus e to the power of minus k times 0. So k times 0, doesn't matter what k is, multiply it by 0, it's still going to be 0. It's minus 0, minus 0 doesn't really happen, but it's just 0, so 0 is 0 is 0. Any number to the power of 0 is just 1. So S multiplied by 1 take 1, which turns out to be 1 take 1 is just 0, S multiplied by 0 is also 0. So when time is equal to 0, the alcohol concentration is also 0. Let's make it time equals 0. What we're told then is to find K when we've been told, when we're given a few bits of information. When our concentration is 5, or our alcohol content's 5, our sugar concentration is 10, and after 3 hours, we're told that A here is equal to 5. So let's set it up. E to the power of minus, I'm going to go 3k. And what we have to do is solve for k. Well, let's go through and try and rearrange this the best we can to see if we can't get our e to the power term by itself. So let's take our 10 across first. So we're going to have 5 divided by 10, which is just a half. So a half is just equal to 1 minus e to the power of 3k. We'll take our 1 across. So we'll have minus a half is equal to minus e to the power of k. So really that is just a half being equal to e to the power of minus 3k. What we need to now do is take the natural log of both sides. Because if we take the natural log of e to the power of any number or any term, it's the natural log of e to the power of any term is just that term by itself. So we're going to have the natural log of a half is going to be equal to minus 3k. And now all we have to do is just divide by minus 3 to find out what k is. And we punch this into our calculator. There's no harm in doing it into our calculator. We'll find that this is roughly equal to 0.231. Roughly equal to, I say roughly, that does continue on, but we'll use that. Now, you might think, why is it a positive number when we're dividing by minus? Well, the natural log of a half is also a negative number. So negative divided by negative will give us this positive. The next part that we need to work out for this is what is the rate of change after a certain amount of time. So to do that, what we need to do is find our derivative. So let's go through and find out what our derivative is. So we'll come over here and set it up again. We've got a is equal to, and we're going to use the same value over as before, so we've got 10 1 minus e to the power of minus 0.231, and we'll leave this as t for the moment. So first of all, we need to work out what our derivative is. Now the easiest way to do that is to first off multiply everything inside this bracket by 10. So we're going to have a being equal to 10 minus 10e to the power of 0.231t. Now let's work out our derivative. So a derivative of 10, and I'm going to call this just a dash for the moment. Derivative of 10 is just 0. Our derivative of e to the power of something, or e to the power of function, is still e to the power of the function multiplied by the derivative of this function. And the derivative of this function here, when we're deriving with respect to t, is just negative 0.231. Whenever we drop the t, it's like saying what's the derivative of 2x? It's just 2. So what we're going to do is multiply minus 10 by minus 0.231. And this is going to be 2.31 e to the power of minus 0.231, sorry. Let's fix that up. 0.231 t. And what we're asked to find is what is the rate of change at 5 hours. So now let's substitute 5 in and find out what our rate of change is. So our rate of change, or a dash, is just going to be 2.31 e to the power of minus 0.231 multiplied by 5. And when we plug all these numbers in, we'll find that our rate of change when t is equal to 5 is going to be equal to 0.728, or roughly thereabouts. So you might come up with a slightly different answer because there is some rounding going on here. But generally, you're going to be expressing your answers in however many significant figures you're given. In this case, we're really only given one significant figure, but it never hurts to go a little bit more. So that's really how we do rates of change with logarithmic functions. We just have to find out the derivative of it. So like before when we did rates of change. It's just finding out the derivative of a function which gives us our rate of change. The hardest bit about something like this is not knowing when we've got unknowns in there. And as you can see, all we have to do, if we've got e to the power of something, take the natural logarithms of it, and we'll get rid of the e to the power of something, so we're just left with minus 3k in this case, and we can just crunch numbers on a calculator to find out what k is. So the next one we're going to go on with is optimization. And I'll just clear the screen and we will be back.